The next thing we're going to look at is the study of chemical kinetics. How fast do reactions proceed and why? In chemistry, one of the key things we want to do is speed up a reaction that's of interest or care about. To take one example, nitrogen is 80% of the air we breathe, but it's very, very hard on its own to take that nitrogen and turn it into a useful form. Ammonia, which might be a common starting material for both fertilizers and explosives. The Haber-Bosch process was able to do that, and that required using sort of the knowledge of chemical kinetics to find a way to speed this reaction up so that it could actually be done in a useful amount of time. So for chemical kinetics, we're going to look at how fast chemical reactions occur, and then just as importantly, or relatedly, how exactly do they occur? What's the actual steps which take us from reactants to products? That'll be the study of reaction mechanisms. So first, the definition. When we're talking about the rate of a chemical equation, just like the rate of any other process, rate of change of position, right, the speed, it's going to be the change in our variable over change in time. So in our case, for the rate of the reaction, we're going to care about the change in concentration over the change in time. We can think about the change in concentration as being the final concentration minus the initial concentration, divided by, again, the change in time, final minus initial. We're going to define our rate to be positive, so when we're taking reactants and turning them into products, we'll call that a positive reaction rate. When we think about the rate of a reaction, the definition we gave before in terms of change in concentration over change in time is really the average rate. What we're going to care about or think a little bit about more directly is this instantaneous rate of change. So that, if we draw a graph, is the slope of the tangent line at a given point. So right here we have a steep slope. That's a fast rate. This is a less steep slope, so a less fast rate. Great thing to think about in, say, Calculus 1, or maybe even a little bit in pre-calculus. For our purposes, though, just important to know that the rate is basically related to the slope there. When we're doing this in lab, say when we're doing the kinetics experiment that you have performed or will perform shortly, what we want to do is keep the average, keep the change in time interval that we're measuring pretty short so we get a good approximation of that instantaneous rate. Now, when we define the reaction rate, we could measure any two species or any specific species. But what we want is to have a consistent way to define the rate of the reaction, so it doesn't really matter which species we're talking about. So in this case, if we look at the coefficients from the chemical equation, there's a coefficient of 2 on HBr. 2 moles of HBr react to produce 1 mole of H2 and Br2. So HBr is going to be consumed at twice the rate that H2 or Br2 is produced. That's, again, just back to our stoichiometry content. 2 moles of HBr is equal to 1 mole of H2 is equal to 1 mole of Br2, because we use the coefficients from the balanced chemical equation to relate reactants to products. So we're going to define the rate of the reaction here as the change in H2 over change in time. And what that means is because H2 and Br2 have the exact same coefficient of 1, Br2 is going to be produced at exactly the same rate. So change in H2 over change in T is equal to change in Br2 over change in time. And that's also going to be equal to negative 1/2 the change in HBr over change in time. We need the 2 here. That's the coefficient from the chemical equation. So that's where this 2 is coming from. And we need the negative because it's a reactant, because when we're producing these two, we're going to be consuming HBr. So the negative is just because it's a reactant. So anytime we have a reactant, we need that negative sign. So our formal definition is shown here for that generic reaction that we're going to sometimes think about in this part of the class. A moles of A plus B moles of B goes to C moles of C plus D moles of D. The overall reaction rate is defined as we take 1 over the coefficient times the just change in that substance over change in time. And we apply a negative sign if it's a reactant. So because the change in concentration over change in time for reactants are negative, we use a negative here so we get that same positive overall rate no matter which substance we're thinking about. Okay, so an easier way to do this than to uh, use that sort of unwieldy equation that we looked at in the last slide is to think about this whole thing as being, our normal stoichiometry, but also just emphasize that this whole thing is equal to 1 mole of reaction. And to also think about that, remember, we have reactants being consumed and products being produced. So let's see how that stoichiometry-based approach works. I think it's a little bit easier and lets you just relate it to your prior chemistry content. So our example, we have 2O3 being decomposed into 3O2 molecules. If O2 is decreasing at a rate of 0.3 molar per second, O2 is increasing at what rate? Well, again, since O3 is a reactant, it's no surprise then that O2 as a product is increasing at a certain rate. Just knowing that, reactants are consumed, products are produced. The idea then is we look at this and we say, okay, this whole thing is equal to 1 mole of reaction is equal to negative 2 moles O3 is equal to 3 moles O2. That's our stoichiometry conversions. Now, when we're thinking about the rate of change, we do include this negative here. So because O3 is a reactant, we'll put a negative there just to emphasize that its rate of change will be negative when there's a positive rate of change of products and a positive rate of change of the reaction. So our idea here, if O3 is decreasing at a rate of 0.30 molar per second, we can just do a normal stoichiometry conversion. We start with O3. So in this case, O3 is decreasing at negative 0.30. Decreasing means the rate of change is negative, so negative 0.30 molar per second of O3. Molar always has a substance associated with it, so it's fair to put the O3 there. That's our given substance. We want to get to the desired substance by doing a stoichiometry conversion. So then we're going to use a stoichiometry conversion factor. And since we want to get to O2, we want to get to O2 molar of O2 per second. The idea then is that we have O3. So that's, again, remember, we think about those conversion factors. We always want to put the thing we want on the top, the thing we have on the bottom. So we have O3, that's going to need to go on the bottom. So negative 2 moles of O3. We want O2, so that's going to go on the top. 3 moles O2. Then again, just like normal with stoichiometry, I can check that my units all cancel. O3 is going to cancel out here. Again, since molarity has that built-in moles of substance on top of it, so the mole, it'll still be molar O2, but O3 cancels, and we do end up with molar of O2 on the top there. When we do this, we have a negative here from the decreasing, a negative here from O3 being a reactant, and a positive here. So times 3 divided by negative 2 gives us 0.45 molar per second. Again, you can always see the sign here just by using common sense. O3 is a reactant, decreasing, O2 as a product, increasing. So the rate of change of O2 has to be this positive number. Reaction rate, again, in this case, remember that now we introduce this idea of this whole thing being equal to 1 mole of reaction. And then the reaction rate is just a conversion factor where we start from whatever given we want, and our desired is going to be molar of reaction per second. And so I can use either one. Maybe I'll show the example with molar of O2. So I'll start from 0.45 molar per second of O2. Then do my conversion factor. I have O2 this time, so O2 is going to be what goes in the denominator. So I need to put 3 moles of O2, or just 3 O2 in the denominator there. Then I want moles of reaction, so I'm going to put 1 mole of reaction, or 1 reaction, On the top, again, it's always 1 mole of reaction is sort of the new thing we introduce, and that gives us a very simple final answer. 0.45 molar per second times 1 over 3 gives us 0.15 molar per second is equal to the reaction rate. And again, if I introduce this convenience of thinking about one reaction as being the unit here, then I'm good. And whenever I get a molar of reaction, that's referring to the overall reaction rate. Again, I can double check that things cancel appropriately, which they do. O2 cancels out there. And again, another check is that the final answer here always has to be positive. So I have to have a positive reaction rate. If I had started from negative 0.30, I would have used -2 down here. And either way, I would have ended up with plus 0.15 molar per second is my reaction rate. So you can always double check by thinking it through logically. Okay, next that we have that definition, we can take a minute to do this example. Calculate the rate and change of A and the overall reaction rate during these time intervals. Okay, next we'll show the solution. So for the interval 0 to 5 seconds, we can say that we're going to use the definition. So the rate of change of A, what that means is delta A over delta T, which is A final minus A initial over T final minus T initial. In this case, the interval is 0 as my initial and 5 as my final, so I'll plug those values in. This is going to be the concentration of A at 5 minutes, 0.61, minus the concentration of A at 0 minutes, which is 1.00 molar, and then the time is 5 minus 0, or again, the delta T interval here is 5 seconds. This shows what that looks like on the calculator, 0.078. And the unit is molar per second, just dividing molar by seconds. That's always the unit on rate that we're going to use, concentration over time. Because A is a reactant, it makes sense that its concentration is decreasing, so it's a negative rate of change there. You can always sort of think about that. Now the overall reaction rate here, one way I like to think about getting from the rate of change of any particular substance to the overall reaction rate is to think about calling this whole thing like a reaction. So the reaction here is A goes to 2P. So if we think about saying that one reaction or 1 mole of reaction is equal to 1A is equal to 2P, we can convert from the rate of change of A to the reaction rate by multiplying by 1 reaction over 1A, where the only difference is because we have that negative sign out here, we do need a negative coefficient here as well. So we do need to account for the fact that that negative for reactants idea here. Again, remember that we always define the reaction rate to be positive, and that will then give us an overall reaction rate of 0.078 molar per second. So B is done the same way. I'll skip to the answer, subtract the concentration at 25 seconds minus the concentration at 20 seconds, divide by that same 5-second change in time as shown here. The rate of change of A is negative 0.0116 molar per second. And then again, we're just basically dividing by the coefficient and making the number positive. So the overall reaction rate is going to be equal to just positive 0.0116 molar per second, because the coefficient on A in the balanced reaction is 1. A is the faster rate, and that is typical. The reaction is going to normally slow down as a reactant is used up. Not always, but usually that's the case. Okay, so here's our next example. Note that you can solve these problems for the most part with stoichiometry. So take a second to try to think about how that works. Try it out, and then I'll show the solution. Okay, so for this one, I'm going to do B first, because here it's easier to think about the stoichiometry involved. So again, I have the ammonia concentration changing at 0.050 molar per second. So for B, the rate of change of hydrogen. So in this case, I want to convert from, again, sort of molar of ammonia, which is NH3 per second, and I'm going to try to convert that to molar of H2 per second. So again, that's just a mole-to-mole conversion factor, so I'm going to start with 0.050 molar per second of NH3, and I'm going to multiply that by, okay, how many NH3 do I have if I look at the coefficients? So my coefficient on NH3 is 2, and it's a product, so that's going to be 2 NH3 down here. The thing that I have goes on the bottom. The thing that I want is H2. So H2, it looks like, is consumed at 3 halves. 3 H2 are consumed for every 2 NH3 that are produced. So this is going to be a -3. Again, just to highlight. -3 H2 are going to be used up for every, are going to be consumed for every 2 NH3 that I produce. So that means my rate of change of H2 is going to be 0.05 times -3 halves is equal to -0.075 molar per second of H2. Again, H2 is a reactant, so we know its rate of change should be negative. Same thing for the rate of change of nitrogen. In that case, I can start with my 0.050 molar per second of NH3 and multiply by, again, using my sort of trick, -1 N2 over 2 NH3. Again, the 1 comes from the fact that the coefficient here in the balanced chemical equation is just 1. The negative comes from the fact that N2 is a reactant. So that's going to give me -0.025 molar per second of N2. And that matches what I see on the graph. NH3 is changing at this sort of positive rate. N2 is changing at a negative rate, but it's not as steep of a slope. And H2 is changing at a negative rate, but at a steeper slope, where the slope here is 1/3 of that slope. For A, remember a good trick is to just write reaction somewhere here. Maybe technically I should write it as a reaction, so 1 mole of reaction, because we know it is always going to have a positive sign at the end. So I can take 0.050 mole of molar NH3 per second times 1 reaction over 2 NH3 is equal to 0.0250 molar per second for the reaction rate, or the overall rate of the reaction. Again, it ends up just sort of dividing by the coefficient, but you can think about it in the exact same way as we did before. Reaction rate's always positive, which matches what we've seen here. And because the coefficient for NH3 is 2, we have to divide by the 2 NH3 in the same way that we have to do that for these other examples. We've defined the rate of a reaction mathematically and shown how stoichiometry can relate the rate of production of products to the rate of consumption of reactants. Now let's introduce our theory or model for how a chemical reaction occurs, simple collision theory. It's these 3 things that are going to have to happen for a chemical reaction to occur. Definitely write these out in your notes, and we'll talk about the meaning of each one, sort of what is the consequence of each of these factors going forward. First, the reacting partners, or the reactants, must collide. The collision must occur with a minimum energy, and the partners must collide in a certain orientation. So the first factor here is that in order for a reaction to occur, there must be a collision. So the upper limit on the rate of a reaction is just how many collisions we have per second. So the collision frequency or collision rate is the number of molecular collisions per second. So if the reaction is A plus B goes to products, and let's say I know that how this reaction occurs is A collides with B. In that case, where I know the exact collision that takes place, I can say that the collision frequency is proportional to the concentration of A times the concentration of B. The more A, more collisions per second, the more B, the more collisions per second, and it's a direct proportional relationship. So if A doubles, the collisions per second will double. If B triples, the collisions per second will triple. Again, that's the meaning of that direct, or again, as we'd say in method of initial rates, first order relationship between collisions and the concentration. When we make this equals, we use a factor of z0 to account for the size of the two molecules. It turns out that that is a huge overestimate of the rate of chemical reactions. Almost every collision that occurs in a particular container does not cause a reaction to occur. It turns out that only collisions that have enough energy result in products. The particle's energy is related to temperature, as we saw in our previous set of notes about intermolecular forces and simple kinetic molecular theory. So at a low temperature, there's only a small number of particles that have enough energy to clear that activation barrier, but at a high temperature, many, many more particles have enough energy to react. And this is not a small effect, it's a huge increase in the number of high energy collisions that you get when you increase temperature, even a small amount. It turns out that it's this exponential relationship shown here, so the fraction of particles with enough energy is given by e to the negative EA over RT, where EA is this important factor called the activation energy. R is the ideal gas constant, and T is the temperature in Kelvin. We'll see the consequence of this equation in a minute. When we combine these two terms, we get a new upper limit on the rate of a chemical reaction, which is shown here. So we have the collisions per second times the fraction of particles with enough collision, gives us this new estimate of the rate. It turns out that this is still too high. It turns out that the molecules must also collide in the correct orientation. So that's what's called the steric factor, which we denote by the variable p. So steric means related to spatial arrangement, and p is just the fraction of collisions which have the correct orientation for a reaction to occur. So when we add that in, the rate is p times z0 times e to the negative EA over RT times A times B. So to get an understanding of what that steric factor is, let's say this reaction we're trying to form the product Ki. So if the K atom hits into the I, a reaction is going to occur. But even if the K atom has a huge amount of energy, if it hits into the carbon here, it's not going to be able to form that K to I bond that we need, and it's not going to cause a reaction to occur. So we don't generally deal with this unwieldy equation. What we do when we get to use chemical kinetics is we wrap up all of these terms out front into one number called the rate constant K. So the rate constant K is going to depend on temperature. We see that right here in the equation, that K varies with temperature according to this term with the activation energy in it. The presence of a catalyst is also going to affect K because that's going to affect the activation energy, as we'll see in a second. But note that K is, the way in which K is constant is that the reactant concentrations have no effect on K. So we can double or triple A and B, and the only effect on the rate is related to the concentration. The rate constant is sort of a separate factor. One of the key equations we can work with is that Arrhenius equation, K is equal to A e to the negative EA over RT. We have this value A, which is the pre-exponential factor. T, again, temperature in units of Kelvin, so we have to take degrees Celsius and add 273, or more precisely, 273.15 to get from Celsius to Kelvin. And R is the gas constant, 8.314 joules per mole Kelvin. Note that we haven't said the units on the, we said the units on the activation energy. Those are joules per mole is what the units should be there. But there's no units given for A or K. So A and K have the same units, but it's going to depend on the reaction, what the units of A happen to be. The Arrhenius equation can be interpreted nicely with a reaction progress diagram. So this shows energy on the y-axis and the reaction coordinate, or we can view that as the reaction progress on the x-axis. So that's showing on the far left here, we start with reactants, in this case NO and O3. We're thinking about the collision that's occurring that's going to take us to our products, which are NO2 plus O2. So these two things come together. It turns out that for this reaction, the best way for it to happen is for them to collide in this sort of head-on way. That's going to be set up to form a bond between this oxygen and this nitrogen atom. And that's our, what we call either activated complex, we have right in the middle here, or again, another name for this is the transition state. Right at that transition state point, we are in the middle of forming the new bond and breaking the old bond in our reaction, and that's the highest energy point along this curve. So we could think about it as sort of like a ball rolling on a hill. We start here. We have to put energy in, so this collision needs to have a certain minimum amount of energy in order to partially break this bond and partially form the new one. Then we go downhill to our products. In this case, this shows us that the reaction is exothermic. It releases energy as we go to our products, forming stronger bonds in products than the ones we're breaking in the reactants. And another thing it gives us here is that forward and reverse activation energies have to be related. So this is the activation energy in the forward direction. The reverse reaction, it's just the distance from the products back to that same highest point. So it turns out that there's no way to only affect the rate of the forward reaction. Whenever we affect the rate of the forward reaction by, say, decreasing the activation energy, we also speed up the reverse reaction. An important point that will come up again when we think about equilibrium. So these reaction coordinate diagrams can give us information about the relative rates of different reactions. So here, for example, let's say we have two similar reactions or different pathways for a given reaction, perhaps. This first reaction here has a given activation energy. The second reaction has a higher activation energy. That means that fewer particles are going to have enough energy to clear that barrier, right? If you think about like popcorn bouncing around, a lot harder for that popcorn to bounce over this high barrier than to bounce over this low one. So this reaction is going to occur much slower, reaction number 2. The higher the activation energy, the fewer particles have enough energy to react, and therefore the smaller the rate constant. Again, remember our equation. It's a little bit hard to view in equations, but you think about the meaning of it. K is A e to the negative EA over RT. This term right here is the fraction of particles that have enough energy to react. The bigger EA, the fewer particles clear that activation barrier, and the smaller that K is. So that's the relationship there. Larger activation energy is a smaller rate constant K, and therefore a slower rate, because again, rate is equal to K times some other stuff. So rate is always directly related to the rate constant K. We can look at how K varies with temperature. That's going to give us really important information about the activation energy of our reaction. Here we can see that this relationship is highly nonlinear. It goes from this pretty small rate constant to a very, very large rate constant as we crank up the temperature. So use the Arrhenius equation to try our first example problem. Pay careful attention to the units because there's a lot of different units and unit conversions you'll need to do here. Okay, so here's my solution. Again, we have the Arrhenius equation now, so the equation we're thinking about is that the rate constant K is A e to the negative EA over RT. The main thing we need to do is make all the units match here. So the first thing is that EA here, to match the units on R is 8.314 joules per mole Kelvin. So we need to get EA in joules per mole in the same way that when we worked with nanometers, for example, with wavelengths, we had to convert that to base SI units before plugging it in. So same idea here. Convert from kilojoules back to normal joules. Another key point here is that whenever we have R, we have to use temperatures in Kelvin. So R is joules per mole Kelvin. So we need to use our temperatures in Kelvin when we plug in. Okay, so plugging into the Arrhenius equation here, A 2.6 times 10 to the 12 per molar per second. Another key point to think about here is the units. So A has units. Anytime we take e to some power here, so this is an important point, e to the anything is unitless, or just a unit of 1. That's important here because then that means the units on K are just given by the units on A. So that's something to think about when you get to the end of the problem. Next, let's plug into this right-hand side with all of the e to the negative EA terms. So we've converted from 31.7 kilojoules to 31.7 times 10 to the third joules. Again, kilo means 10 to the 3, so times 10 to the 3 would work to plug that in. Negative 31.7 times 10 to the 3 joules per mole divided by, again, we've got our value of R, 8.314 joules per mole Kelvin. Our temperature is in Kelvin, so we'll plug that in. It turns out that that temperature in Kelvin, 25 plus 273.15, is 298.15 Kelvin. And again, all of our units do match here. You could go and double check that if you wish. The Kelvin here cancels. Kelvin cancels, and then joules per mole on top and bottom cancel as well. Turns out, again, that anytime you have something in an exponent, everything inside of that needs to be unitless. So all the units need to cancel, which they do here. Okay, next let's go through and show the solution. So in this case, again, there's no algebra to do. We have the thing we want on the left, so we just plug everything in. So 2.6 E12 times e to the, again, negative 31.7 E3. You've got to find that e to the power of up there. So in this case on the T84, it's the second ln to find that key. Might be in a little bit different places on your calculator. Again, we've got two things in the denominator, 8.314 times 298, so you do need those parentheses there to make this work. And here, again, you could move this decimal place yourself 6 places, or as you'll see, you could convert to sort of scientific notation here. Your calculator does have a scientific notation mode that would make that a little bit easier. But yeah, our final answer here, 7.3 times 10 to the 6th. And again, the unit on K matches the unit on A. So 7.3 times 10 to the 6th per molar per second. Okay, for the other one, all we're doing is plugging in again, but at a slightly higher temperature, so we'll skip through that pretty quickly. The only thing that changes here is that 298.15 switches to 308.15, so you can even just use the up arrow key on your calculator to go back one, and then just line edit from 298 to 308 and quickly get the correct answer. In this case, we're moving it 7 places to the left, so this exponent is 10 to the 7. Again, this is really potentially error prone here, so it's a good idea to switch to scientific notation mode for this type of problem. That's under mode here, so mode scientific. That will then show this as just 1.1 times 10 to the 7. Always an option there so you're not potentially missing decimal places when you're moving things around. Same idea for another calculator under that mode. You should be able to quickly swap those back and forth. Okay, now we're ready to get to part B. So what happened in the reaction rate? If we look at it, it went from 7.3 times 10 to the 6 to 1.1 times 10 to the 7. If I want to express those on the same exponent, right, 1.1 times 10 to the 7 is actually 11 times 10 to the 6. So this is a significantly bigger rate constant, much faster reaction here. And why is that? Well, it's because when we think about simple collision theory, what's happening is that a greater fraction of collisions are going to have enough energy. And that's expressed in this exponential term, e to the negative EA over RT. So some people think the reason here is because of the increased collisions. Actually, the Arrhenius equation is completely ignoring any increase in collisions. There would be a slight increase in collisions, but only a few percent. The much bigger factor is the fraction of collisions that have enough energy factor, and that causes this quite dramatic increase in rate for just a small increase in temperature. Okay, the next thing is sort of getting to the idea of determining these parameters from experiment. So we showed on a previous slide how k versus t is this very nonlinear graph where k shoots up with temperature. A common approach in all sorts of different kinds of science is when we have a nonlinear equation, we transform it by taking logs or 1 over and things like that to linearize the equation. So we can do that for this equation because we have an exponent over here on the right. We want to take ln of both sides. When we take ln of both sides, we get ln of k on the left. Ln on the right-hand side, we do need to use some logarithm rules to make that work. The key idea there is that when we take ln of two things together, so ln a times b is equal to ln of a plus ln of b. That's what we've used in this equation here to split this into ln a minus e over rt. Again, the thing you need to know from like previous math classes is that if I have, let's say, y is equal to e to the x, to get x out of the exponential there, I have to take ln of both sides. So if I take ln of both sides, I get ln of y is equal to x. So ln is sort of the inverse operation of exponentials. And similarly, if I want to undo an ln, I have to take e to the power of both sides. So those two operations will undo each other. So we need to apply, so that ln is motivated by getting rid of the e to the power of on the right-hand side and bringing that down into just the normal part of the equation. Then what we do is we line this equation up and figure out what kind of relationship we have here. So if we look at this, our dependent variable was k, so ln of k is related to the dependent variable, and that would be a good thing to plot on our y-axis. Similarly, t was our independent variable, so 1 over t here will be a good thing to plot on our x-axis to make this linear. Then we'll see the slope will be negative e over r, and the y-intercept, b, will be equal to ln of a. So again, you don't necessarily need to memorize these relationships. If you look at this equation and just match it up with y equals mx plus b, you should be able to see, okay, ln of k is my y-axis, 1 over t is my x-axis. That leaves my slope as equal to this whole term together, negative e over r, and b happens to be equal to ln of that pre-exponential factor a. Okay, so here's an example applying that equation. Take a look at this data and see if you can determine the activation energy and the pre-exponential factor. Okay, so here's the solution. Again, we're starting from that same point that we know we have ln of k versus 1 over t here. Now we're going to look at that linearized form of the Arrhenius equation, which you'll get on your equation sheet. Again, it's not something you have to memorize here. Ln of k is your y variable. 1 over t is your x variable. So you look at this here and you say ln of k is equal to y. That's sort of one relationship I have here. 1 over t is equal to x. Then that leaves me here with these other relationships. It happens to be the case then that negative e over r is equal to m. So that's one relationship there. And similarly, ln of a is equal to b. We'll keep practicing this with other equations throughout this part of the class, but that's the process there. So to determine the activation energy, I can see that the activation energy is going to come from the slope. So again, I look at my equation line, y equals mx plus b. I can see that my slope m is equal to negative 6,240. Again, when I think about the units here, this does have units. The key idea is that ln of k is unitless because it has that special function in it. So that has just units of 1, just like e to something would be unitless. 1 over t here has units of 1 over Kelvin. And again, remember that when I think about what the slope means, it's the rise over the run. And so the slope m is sort of the delta y over delta x. And the units then are going to be equal to the y unit over the x unit. That's always the case, and we'll keep using that throughout this class. You've used it in lab already, of course. Y unit, x unit, so y unit is just 1, the x unit is 1 over Kelvin. And so m is equal to negative 6240 Kelvin. Just applying that carefully. Comparing it to the model, I see that m is equal to negative EA over R. And so to solve for EA, I'm just going to multiply both sides by negative R. The negative I need to move over to the left-hand side, and I need to multiply by R2 to get R to the left-hand side. So multiply by negative R. And then again, the negatives will cancel, so that just gives me EA here on the right-hand side. Okay, then negative R, so that's negative 8.314 joules per mole Kelvin. M was negative 6240 Kelvin. You can see that the units here are working out nicely. Kelvin on top, Kelvin on bottom cancels. And my final answer here will come out as, final answer then, 51,879 joules per mole. That is the base SI unit for activation energy. Again, it's common to report that in kilojoules per mole, since kilo means 10 to the third or 1,000. I can do that conversion by moving the decimal place 3 units to the left. Again, the equivalent of dividing by 1,000 joules per kilojoule. That's another way of doing it if I wanted to convert to kilojoules. And I get 51.9 kilojoules to 3 significant figures. This just shows that in a dimensional analysis approach, we don't give you the conversion from joules to kilojoules. We sort of assume that you can know that kilo prefix means 1,000. The second part here is solving for the pre-exponential factor a. Again, we can see here that ln of a is equal to b. And so that's the conversion we want to do. So b is equal to 19.2. And again, from this relationship here, we have that b is equal to ln of a. So to undo that natural logarithm, again, remember exponential, e to the power of, and ln are sort of inverse operations. So again, if I had to show that example, if I have ln of x is equal to 0.693, to undo the ln, I take e to the power of both sides. E to the ln of x is just x. E to the 0.693, in this case, happens to be 2. So that's a way to figure out ln of what is equal to 0.693. Yeah, it happens to be e to the 0.693, which is 2. So same thing here. Applying that, I need to take e to the power of both sides to undo the natural log. So e to the power b is equal to, again, e to the ln of a is just equal to a. B was 19.2, and it is a unitless number. So e to the 19.2 is equal to a. I can plug that in. I've got to convert back to scientific notation to make that work nicely here, so I don't have to move the decimal place so many places. I then get 2 point, what do I have? I've got, yeah, since this is an ln, I maybe only get 2 sig figs, but we can go with 3 sig figs for now anyway. That would probably be fine. 2.18 times 10 to the 8. The units here are going to depend on the units of k. So in this case, it's, say, a first order process. And so the units here are 1 over seconds. Again, sometimes what we'll do is we'll put ln of k divided by seconds to the minus 1, and that will sort of tell us what the units on k were. Ln of k is unitless, but k did have units, and a has whatever units match k there. So that's the idea if we need to solve for the pre-exponential factor. Okay, so some takeaways from this. The Arrhenius equation relates the slope of ln of k versus 1 over t to the activation energy and the pre-exponential factor. Again, typical to see activation energies in units of kilojoules per mole, typically 1 to 100 or 200 kilojoules per mole. Make sure to keep track of all your unit conversions. And again, this is for a sort of solar cell material that shows Arrhenius behavior. All sorts of reactions, not just simple solution or gas phase reactions, show Arrhenius behavior. Now that we've dealt with some of the math, here's a little bit more on the role of catalysts according to the Arrhenius equation. So here's our definition of a catalyst. It participates in the reaction, and it decreases the activation energy, which causes the reaction rate to increase. And most importantly, it's not consumed by the reaction. Another way to say that is it's got to be regenerated during the reaction. So it's maybe going to participate, get temporarily used up and converted into something else, but when we make our final products, the catalyst is going to be regenerated back to the original catalyst molecule. We have some definitions. Homogeneous is the same phase as the reactants. Heterogeneous, that would be a different phase than reactants. Often, like a solid metal surface can catalyze either gas phase or aqueous phase reactions. So that's an example of heterogeneous. Enzymes, again, maybe they're homogeneous, but they're large molecules that catalyze specific biological reactions. They work in a little bit different way than most of the catalysts that we use other times in lab. Again, they're very large molecules. They're often only stable under very limited conditions, certain pHs, certain temperatures. So we have to hone the reaction conditions to exactly where the enzyme is going to work the best if we want to use an enzyme catalyst. Okay, so here's an example showing what happens with the bromide catalyzed decomposition of hydrogen peroxide. So we add the bromide via NABr or KBr. And when we do that, we see a color change. So Br minus is colorless, but when we add Br minus, we see this yellow substance formed. That's indicating that that's coming from the Br minus ion and its new form that it's taking on to catalyze the reaction. So it's showing that the catalyst is participating in the reaction. We've got bubbles to show the production of O2, so the speed of the reaction is greatly increased. At the very end, everything is decomposed and the catalyst is back to its initial form or color. So a nice example of how a catalyst acts to speed up the reaction, participate, and then gets regenerated at the end. It turns out that the way this process occurs is via this two-step type mechanism. The yellow color is caused by the production of a little bit of Br2 liquid. We'll see more about these individual steps by which a reaction takes place when we get to reaction mechanisms, the last topic on exam 2. So this is responsible for our yellow color. And again, once we use up all the Br2 liquid in step 2, the yellow color will disappear. So again, showing what that looks like, a reaction coordinate diagram is a great way to see that. We can see that the uncatalyzed reaction here has a high activation energy, so therefore a slow rate and a small rate constant K. When we add the catalyst, again, think about our popcorn bouncing around. Only a few kernels had enough energy to get over this large barrier. Here, a lot more particles have enough energy to get over that barrier, so many more collisions will cause a reaction to occur. Again, we can often use either homogeneous or heterogeneous or enzyme catalysts to catalyze the same reaction. Here's an example of an enzyme catalyst. Again, this is a gigantic molecule, but it's arranged to remember the whole point of catalysts is that they're going to need to lower that activation energy. So we've got an activation energy EA. According to our transition state theory, to lower EA, what we need to do is take that transition state and stabilize it. So these enzymes are designed to exactly help out the molecules in that least stable arrangement and provide them a little bit of extra stability when they get there. So if you're able to sort of hold the molecule in place in the right way and form some interactions with each reactant to stabilize them a bit in that most unstable configuration, the enzyme is then able to lower the activation energy and speed up the reaction, in many cases by a huge factor. So here's an example. Again, we looked at the bromide ion catalyst for H2O2. We could use a heterogeneous catalyst, which you might use if you use the hydrogen peroxide containing contact solution. That uses probably some silver particles there to catalyze the reaction and speed it up significantly. Then enzyme catalysts also work. So catalase is a liver enzyme, and it's the first catalyst that was discovered. That's why it's called catalase rather than just, hydrogen peroxide ACE or something like that. It catalyzes the decomposition of H2O2 because H2O2 is incredibly destructive and harmful in the human body or, in any cell. It acts to destroy a lot of the different molecules in the body. So as a result, life has developed this incredibly efficient enzyme to immediately get rid of H2O2 before it causes problems by wrecking other things in the cell. So this catalyst very efficiently converts H2O2 into just harmless water and oxygen. Okay, so here's our example looking at sort of enzyme kinetics and reaction coordinate diagrams. Take a minute to try this, and then I'll show the solution. Okay, so this case, the first key information we have is that it's exothermic. So exothermic means it releases heat. This is review from prior chemistry, but again, what that means is that the reaction is sort of downhill. The reactants are going to be higher, and the products are going to be lower in energy. Again, we always draw reactants on the left, products on the right in a reaction coordinate diagram. Then the initial reaction is going to be pretty difficult to occur because it's uncatalyzed. The activated complex or transition state is up there. That's that highest point on the curve. Then an arrow representing the activation energy. So the activation energy is the distance from the energy of the reactants up to the activated complex. So this is the activation energy. We can see also on this graph that the reverse reaction is going to have a much bigger activation energy because, again, that would be from down here all the way up to that same peak. Next, we're going to draw another curve showing the reaction's path in a car's catalytic converter. Note the word catalytic, so catalytic converter is a catalyzed pathway for the reaction. I'll maybe draw that in blue here. Same reactants, same products, but the difference is that the catalyst stabilizes the transition state or stabilizes the activated complex, lowering the activation energy. So maybe it stabilizes it like this, and that's our new pathway. So this is B, the catalyzed pathway. Again, if I look at the activation energy, it's much lower. E, A, catalyzed, is this much lower activation energy. That's going to explain why the reaction becomes much faster. This set of notes has quite a bit of new mathematical and conceptual material, so here are the summary slides giving you something to review as you're starting to work problems in this area. Simple collision theory, this is our key conceptual new piece of content, but it also is related to some new mathematical content, the Arrhenius equation, as shown over here on the right. The other new thing we introduced here was this idea of comparing models to a linear plot. You have done that in lab already, but now you're expected to also be able to do that in class. Again, if you compare the linearized equation to the equation of a line, you should be able to line up what is the slope, what is the y-intercept. Again, remember how units work on these graphs here. Slope unit is y unit over x unit to figure out the units here properly. This will also come up when we do new content on integrated rate laws coming up here.